Okay, so I'm going to come in and demo today my operating system that I've been developing. Obviously, that's not something that is PHP related or what we do generally, but it's a side project and it has been a hobby of mine for a while. It's also what I went to school for, and it's been kind of fun to get back into it and start re-exploring what I've been doing. So I pasted it into Slack here, and if you're watching this on a YouTube video, you'll see it in the YouTube video comments, a link to the operating system source code, along with some pointers on where to go if you want to get started and into this. The point of developing an operating system really isn't to replace Windows or to replace your Mac OS. It's to experience and to get to know the base level of the computer so that you can start to really have a better sense of how to develop code, how to do things in general. In particular, and related to what we're doing, it's made me a better coder and a better product manager for a number of reasons. First, I have to think about the small stuff. The small stuff really matters. I have to look at where the ones and zeros are. That controls where the bugs are, right? So if I'm thinking about small things, I'm thinking about the big picture and how those small things impact everything else down the road. That applies directly to everything that we do in product and engineering land with PHP. Second, debugging is crucial to the operating system. It's a really important skill, and you can't do OS development without low-level coding and low and expert debugging skills. So that means connecting in via the GDB command line, outputting key info, interfacing in different ways to get it done. And second, and the third thing about all this that makes me a better programmer and product manager overall is that it forces you to get creative. You have to really think about the way that stuff interacts with things. You have to find ways around stuff. There is not a single path that you have to take in the vast majority of operating system coding and design. So if you want to get to a point where you can put a pixel on a screen, you're going to have to figure that out and really get creative in the way that your functions are being called, in the way that everything else is moving on, so you can get that pixel on the screen in the most effective way possible. And finally, that brings me to my last point of why this is something that everybody that codes PHP and is in product management should really think about, is it forces you to optimize. I have 921,600 pixels on the screen in my operating system. I need to be able to draw on those really, really fast. If I just have a single function call called putPixel that gets called almost a million times every time I want to refresh the screen, that's never going to work. That's a ridiculous solution in an operating system land. So I have to figure a way to optimize that and to get it moving forward. So that being said, let's take a look at what the actual operating system is. Now, browse on your own, browse the code and everything, but I want to kind of go through and at first just show you what it looks like, and then walk through a couple key segments that I think are kind of interesting. To begin with, everything is done in C and C++ and it's an x86 assembly. I have a cross compiler built on my Mac that allows me to run all this stuff and code it for a x86 system that is different than any other computer out there. I've built a lot of makefiles and shell scripts that allow me to do things like this. Enter one command, have the operating system boot, and then have it display here on the screen. We can see from this screen then that we have, it's pretty simple, right? We have a command prompt up, we have a secondary console, and we can do things. We can see a list of commands that come up. We can run a little short program that I've written that we'll talk about more later, or we can take a look at memory and see what some memory looks like at the beginning of the operating system. Now, what's interesting here is that everything that we're doing, from displaying text to looking at things, all of these routines, I've actually had to go in and write. None of this comes prepackaged anymore. Because it's an operating system, you don't have your library C available to you. You don't have PHP routines that you're typically used to. You don't have anything and any components that are going to actually do anything. So you have to code every single thing that you do. Even the mouse that you see on the screen right now, this is an operating system mouse that I've coded myself, and you can see it works pretty well. It replaces the pixels in the background, it moves around the screen and everything. It even has click events, which we can't see right now, but still, that's had to been coded too. And even through the magic of a system, I can actually quit the operating system and return to my environment here. So let's talk a little bit about what actually goes into this, because really this is all about interacting with low-level stuff, right? So at the basic level, we have a system that boots in via grub. We're all used to grub. We're familiar with it from setting up our own Linux systems. Only difference is, instead of going to Linux, we send grub over here to my custom kernel and operating system that's being developed. That actually starts right down here. So grub enters the area right at start one. That's the primary function. How does it know it's the primary function? Because it uses the GCC linker script to know that it needs to enter everything at start one. It knows that also start1s is starting at a particular address as well. It's starting at the 1000 address right there, or 10,000 address. So start1, what happens? Well, initially we need to set up what's called memory paging. I won't get into what that is, but it basically lets you, at the end of the day, turn on virtual memory. So you can say, even though this little bit of code rests at memory location 5000, what if I want to think about this code being accessed at address 0? So that's what paging allows us to access that code at 5000 by putting in 0, right? It's a little weird, a little hard to wrap your head around, but it's also very crucial. This also illustrates one of the more interesting parts besides what that is, in that this code right here that I'm highlighting, these 6 lines of code, that's basically what every operating system, what every computer in the world that's running x86 does at the beginning. It executes these 6 lines in order to set up paging correctly. That's pretty neat, I think. Like, this is what's happened since the 386 was introduced all those decades ago, right? This 6 lines are what you need to perform modern operating systems. Now, after we get there, we jump down to the next start routine. It does some more stuff. It jumps down to another start routine after it sets up pages. And then finally, we get down here where we end up calling the main kernel function. The main kernel function drops us over into the C code in this guy, and then we actually start to do some fun stuff. We start to set up the memory, we start to set up a serial port, we set up the terminal, and we begin to output things. Now, one of the cool things that I've done with my operating system is set up the serial port to automatically output on my terminal. So in the emulator where the operating system boots into, I'm able to have the serial port get output right to the standard input-output on my Linux console here. So this is where we're able to see some debug information, and we see these things here via the function that I made called debugf that takes everything here, puts it through the serial port's bit processor, and dumps it out in this guy. So one of the things that makes my operating system a little bit unique already is that I've been able to enable VGA programming. This is one of the more interesting parts about it, so let's take a look at what VGA does. VGA is everything that you see on the screen, right? If you've coded in the 90s anytime, you would know that you have to make commands to draw a line and everything like that. So we actually do that quite well in the operating system here. You can see there's a lot of commands and a lot of really meaty stuff to just place a pixel on the screen. At the same time, though, we get down to some interesting things like drawing a character on a screen. So to draw a character, we have to go through a bitmap character routine that looks at each row and each column, determines if the pixel of the character is going to be placed at the right pixel on the screen, how that pixel is going to interact, what should be replaced, what color that should be, right? And so we do that all in this draw character routine. The interesting part about this draw character routine is that it doesn't actually call anything else. It's highly optimized. Again, that optimization thing I was talking about, this is where the optimization takes place. If we're going to be drawing hundreds and hundreds of thousands of characters on the screen in a big screen, we need that to happen really, really fast. So we literally are computing the exact memory offset of where those pixels need to be placed for the character, looking at a bitmap segment of the character and then placing the pixels immediately. We're not calling any other routines. We're doing a lot of complicated pointer math, a lot of other things that are sitting there in C++ land that are rather esoteric to that language. Now, the same thing happens when we want to fill a rectangle on the screen. Remember, the memory, and we deal with this all the time in PHP, it's just a series of contiguous bytes, right? So what we do when we fill a rectangle is we simply look at the bytes that we want to fill. In this case, at the beginning, I blank out the entire screen, and then it just fills that color in. It doesn't call another function or anything, but what it will do is just set that exact byte to that exact color. We go to the next line and repeat the process over and over again for whatever the dimensions of the rectangle are. This ends up being very fast since the call stack and the way that the operating system is interacting with is just executing the same assembly code over and over again without going and jumping to any other place. So in PHP land, your takeaway from this would be, if I can get away with not having a useless function, don't have a useless function, because guess what? That's causing you to jump. That's causing the processor to switch contexts to another function, where if instead it can just be done here, great. Now, that always isn't possible, of course, especially when building things like unit tests, but where it is possible, it's interesting to think about it from an optimization standpoint. So that's what the fill rectangle does, and that's how we kind of deal with our putting pixels on the screen. Another interesting way that I'm trying to develop the operating system is really have it be agnostic compared to, in terms of whether or not it wants to use a graphical terminal or whether it wants to use an actual text terminal. So over here in my make file, I actually include some commands that let me turn off graphics. So right now we have an enable graphics command. That means that we're going to activate the VGA system. If I set that to 0 and go back and build the operating system again, rerun it after it's compiled, I see a typical command prompt, and that's pretty cool. So at this point, I actually want to kind of switch gears now and talk a little bit about processes and what my next steps are going to be in this. So one of the big things to do in an operating system is to get processes working, right? A computer is just a bunch of things running together all at the same time. Well, classically, one of the ways to test this is by doing a A/B test, right? So if we can get a system set up that will encourage the processor to switch between printing an A character and printing a B character over and over again, then we know that the process system is worked up. So I have coded something like that here, executing it, and we can see the computer now just constantly spitting out AB, AB, AB. This will run indefinitely. In fact, I left this running overnight one time just to make sure there wasn't any memory leaks or anything like that, and lo and behold, it was. So it's pretty neat. That means that our processor is now able to handle a multi-process system. So what does that actually look like? Well, when you enter the process, it is going to go right over here to our process file. And we see down here, we're taking these, it's called a system break when a process fires. We see that the system break looks at it. We look at what the next process is, determine that. We switch all those registers around, which you learned about in your computer science courses. And then we just simply load the registers with the registers of the next process. And once that's done, we return up the stack, just like you do in a call chain in PHP. And after that returns, it decides to go to the right function or the right process. Remember, a process is just a function, right? So this is where we start off with in our A function where it prints A, it calls the system break, then it decides to go down to B. It calls the system break and it starts printing off down here. B calls the system break, next process is just A, and so it repeats ad infinitum, right? It's kind of neat when you think about it. Now, the final thing that I want to talk about is integrating it with other larger processes, and not processes rather, but other larger things out there in the world. We have a lot of open source code that we can draw upon, and we draw upon this in all of our PHP development as well. But there's a ton there for C development and for operating system development too. One of the ways that you need to do that is by dynamically loading code in. So I mentioned I was going to kind of go back to what the whole paging thing is about, right? So I want to go and talk about that just for a minute and kind of give a little demonstration of what this does. So paging is all about virtual memory. Paging says that if you want to set the virtual address of 0 to actually point to memory address 5000, you can do that. So every time the computer sees memory address 0, it'll actually see memory address 10,000. That's really cool, and it gives us a really effective way then to begin to load external code into our operating system that would want to be placed at memory address 0. And in fact, this is how the entirety of computers and modern computers are basically built. The compiler compiles your program, it assumes that it's going to be located at 0 and expects the operating system to honor that. Well, of course, there's a lot of stuff at 0, right? So you can't just like throw it in there. But if you set up paging and set up your virtual memory to allow it, you're able to do that. So in this case, we are loading this special process through, again, the linker script at this location right here, at location 10000000 in hex. But we have that set up as page directory 0, so it's going to look like it's getting mapped to location 0. Now, the program itself is pretty simple. I'll show it to you. It's just this hello world program, right? The program simply spits out, takes the message in, the address of a message, it puts the necessary system command in the right register, and then it executes a system call that will print whatever is given. So the message that we're going to print here is, I bet this is going to crash in front of all of you, because I bet it will. And what we do then is we're loading this, again, through the linker script at this address, right? This is the little part that does it down here. When this loads, and if this works correctly, it means that we've set up paging to allow external code to be modularly loaded into the kernel and executed. At that point, we're just very few steps away from being able to have a completely independent system. It means that I can very soon build out my own GCC and C compiler to allow for myself to start compiling things and actually coding things inside my kernel and inside my operating system, which is pretty neat. So I'll turn back on graphics here for the full demonstration. Just rebuilt the system, loaded it up, here we are, and if I type the command, and if I don't remember what the command is, by the way, I just can hit the question mark and spit all this stuff out. And so the command here is run it, and if I type run it, we can see that this modular program has successfully been loaded in and actually executes the command. It's kind of neat. And then if we actually want to take a peek at memory address location 0, the virtual memory address location 0, and let's take a look at about 20 lines, we can see there that the code is actually loaded in, and there's the string right in front of us. So this has been kind of a whirlwind tour of what the operating system is, what it can do, what some of the reasons to that we should actually all do this are, right? And I would really encourage you to take a look at some of the links that I provided in Slack and that you'll see on the bottom of this YouTube video, and try to get into it. It's not terribly difficult to make a Hello World program and just display a little bit of text in your emulator screen. I use QEMU. This works in VMware. This works in Bosch. All the other different stuff. It works in VirtualBox, which we all use in our development environments, anyways. And once you're able to do that, you're really able to then start adding more and more and more and more and more. And it really becomes almost a waterfall. Not to mention that word in front of our project management, but it's kind of neat and really has forced me to start thinking about things in different ways, both from product level and from an engineering level, that I think has been rather helpful, especially with some of our recent projects. So that said, that's been a lot of things that I've just gone about, and with 5 minutes left, I wanted to open the floor up to any questions.
Anybody awake?
This is very interesting, Adam. Did you use any existing bootloader, or you have your own customized program?
Yeah, that's actually a good question. So I do use a out-of-the-box bootloader. I use Grub, and that looks like this. I'll just go into the file here in the console. The grub commands that I'm doing are pretty simple, though. So if you look at the grub source file, you'll see all that we do is we simply load the operating system compiled kernel with the multi-boot headers enabled. The multi-boot headers that we use are kind of cool and allow us to place some important information in the kernel, though, and give us a little bit more data when we load up, including things like aligning the memory, which is really possible, a memory map, as well as setting up the original video mode, which is kind of harder, very non-intelligent to do in a normal operating system. So we're really able to do that all through Grub.
So you are feeding a assembly program after the Grub is loaded, right? Or we can execute a C binary directly. Is that possible?
No, that's another good question. So yeah, you actually have to start in assembly. It probably is possible for some way to start doing an initial routines in C, but it's not advisable because you need to do a lot of low-level setup before you get into C and before you start using that functional environment. You need to set things like the global descriptor table, the boot, the boot page directories and everything. So the best way to go about that is to start immediately after Grub loads into a short assembly program, which starts right here at the start one location. And after you've set up all those really important things, then you jump down and call the C program itself.
Cool. So does it work in 16-bit, or it can enter to protected mode as well?
Yeah, actually, this jumps right into protected mode. The 16-bit stuff we can do. You have to actually do this thing called VM86 emulation in order to get into 16-bit, which is something that I don't have coded in here right now. But it's also neat because 16-bit relies on the BIOS to do a lot of stuff, right? And in modern computers, they don't have the traditional BIOS anymore. You just have to interface with the hardware directly. So 32-bit programming forces you to do that. And so far, I've found that it's not too difficult to interface with the hardware directly. You know, I'm interfacing with the serial ports right off the bat. One of the projects that I'm working on right now actually is to interface with an Ethernet controller, so I can hopefully in short order serve up a web page on this, oddly enough. And doing that is difficult in understanding what all the technology means and what all the routes are, but actually coding it isn't too hard once you kind of get the hang of it.
What's the file system on your?
So it all boots up in the EX2 system. That is the traditional Linux file system as well. It uses the object format of an ELF32 binary, which again is ABI compatible with Linux. Eventually, I'm going to design my own file system though, because I kind of want this to be it's not an exercise in being able to boot a Linux program as much as it is just being able to understand everything.
All right, thanks, Adam, and that was pretty good. Any further questions, please pick up on Slack. We are running out of time, so let's move on to our next demo.